Okay, in this section, this lab 6, we'll start to describe the project 2 a little bit more details, and we'll review the code of the project 2. We like the as I described earlier a little bit also in the class, this project requirement is that primary object is to design the system. Forget about this memory 1K. We'll put that as a 256 megabyte of memory, which is basically 64 M data line with 32-bit word size, which the memory I described in the lab 5 section for the memory modeling. But we'll do exactly implement this system, which will actually can take a program written in CS147 DV, of course in the machine code, and execute that program. Okay, so we'll write the behavioral model, or we call it an RTL, or register transfer level model, with this is a very bare minimum computer system, and we do that to kind of refresh our understanding of how the computer works. Okay, the main part of that, the thing you need to do is to implement a register file, which is very similar to the memory modeling, which has been done. ALU we take from the project 1 and extend it to have a 0 flag as an output. The main part, the fun part, is this implementing control unit. Okay, so this is the part where you describe what a computer does inside. Okay, like it brings out the instruction, parse the instruction, know what to do, issues corresponding register read or ALU function, and store back the results, and so on and so forth. So this is the main part. This is the main important part on which the entire functionality is depending. Alright, so we'll review along with the slide the code itself, the same project we created in the lab 5 that we use. That's for the project 2 implementation in the model sim. Okay, the same project we'll use here. So about this test bench structure, what it has, this is in the file davinci_tb.v. Needs to be completed in the sense little bit to which program to be loaded in the system or not, and means this DaVinci system, right, in not, and so on and so forth. So it consists of a test bench code, little bit very small, a DaVinci instantiation of a DaVinci system, and it has a clock generator. What this test bench code issues is a reset signal to the DaVinci system, which has a processor and the memory. You know that our memory on the reset signal, it loads the program. Remember that memint file from lab 5, it loads that file. If we just write some machine code of the program from a specific address, it will load it on the reset. The clock generator is independent and supply the clock signal to both the system test bench and the DaVinci, and everything else, this read, write, address, data, all these things kind of like a probe. It doesn't do anything. We're just interested in observing those signal, what goes inside this DaVinci system on a signal view. So we are probing those signal out of the DaVinci system. Okay, no functionality is there. So let's look at the code of the DaVinci TB. So we start with the DaVinci TB is, we include the project definition file, and also we include let's see, the project definition file is define the time scale 1 nanosecond. This is a time unit, and this is my simulation resolution 10 picosecond, and all the different macros are defined, like mem size, address size, clock period, half clock period. Defines a macro for the states. Process state, we'll discuss this state later in much detail. The start address of the program, and stack pointer, address of the stack pointer, and so on and so forth. Anyway, so the test bench includes that, and then it defines some paths of address to kind of observe the address going on inside the DaVinci system, read and write. We have the clock signal, we observe the data signal, we supply the reset to the register, this thing, and we have we instantiate the clock generator, which supplies the clock, and then we instantiate the DaVinci system, which has the processor and the memory itself, and it is parameterized to pass the which program to be loaded. For example, here we are trying to load the program Fibonacci.dat, that program, into the DaVinci system, so it will load that. We'll review the DaVinci code itself in a minute. And then it initializes the reset at the 1, which is non-reset state. It is reset on low, so at 5 nanosecond it will reset the system. At 10 nanosecond it will just revoke the reset from the system. And here what we need to do, here it says rest of the test goes here, but you can do some fancy tested if you need, but bare minimum thing what you need to do at the end of the program, like we assume okay 5000 nanosecond is enough to execute the entire of your program. It depends on your which program you are testing. Like we put 2 example here program already within your package of zip file, and we do this right at the end of this execution. We do a write mem on the memory dump from the corresponding address on which we know this program is going to write something. Okay, we want to look at the result from this DaVinci memory instance of memory of the DaVinci system, and we have the SRAM inside the memory. So from this part, so this is DaVinci instance dot memory instance dot SRAM. So we are dereferencing till to the point where we are actually accessing the storage implementation of the memory. And the part of the address, start address and end address, we know this Fibonacci program is going to write within these 2 address boundary. So we dump the program, and there is a golden file supplied with this package zip file, which is like Fibonacci dump memdump.golden and refib memdump.golden. So what you need to do, you take the your dump program, your dump file, memory dump file, and compare with this. If your system is correct, this result ought to be looks like these numbers. Okay, so this is one simple test. And also what you need to do, if you want to switch the program, you comment out the previous program, one program, and activate the other program. And while doing that, you also need to change the memory dump. So comment out the previous dump and activate the new dump. This is the dump for the refib program, and you save it and recompile. So once you do it, then if you invoke this tb test bench program, then it will start loading refib.dat program instead of Fibonacci.dat. Okay, so this is the thing you need to all you need to know about the test bench. Okay, so once your test bench is done, then we move to the system itself, which is DaVinci v1.0. So let's look at the system. So it takes input reset and clock and instantiate a processor and the memory, and this is the file davinci.v. Don't need to change it, it is all pre-written for you. So let me just explain that file a little bit. So what it does, the processor either reads the data from the memory or writes the data back in the memory. It issues the address for the read or write operation, and it sets the read and write signal correctly for the memory cycle. So that's all of the processor does. Okay, so the execution is done in this way. Okay, so processor knows what is my next instruction fetch address. So that's basically a memory read. So it sets up the address for that instruction, it sets the mode to the read mode, and then it simply reads the data, whatever data from the memory is coming, which is it takes as an instruction. Now it parses the instruction, do whatever it needs to do inside there. At the end of the day, it's most probably if it involves a store word, okay, which basically all the program needs to store the result back in the memory, then it issues that store word address where data needs to be written. It push out the data and it sets the mode to read equals 0, write equals 1. So that's the write mode, the result is written back. Now if the instruction is load word, which is reading the memory, so load words also involves it supplies a data address, okay, so it takes the address, issue the address, set read equal to 1, write equals 0, and memory issues the data, it reads the data back and do something with that. So that's all the processor actually does, okay, at very basic level. So now if you see, this is the self-contained system. We just need the reset and supply and clock signal. It is almost like the power button of your laptop, or you can just imagine that. It is a little bit complex in the real life, but it's just equivalent thing. Or a desktop, you have the power button, you just turn on, it issues a reset signal. Yeah, powered up issues reset signal, it gets thing going. So the output, write, read, and address, this is just kind of, you can see we are just probing them out. This is nothing to do with the functionality, probing them out towards the test bench. And in the test bench, it's just we are observing the signal in the signal window. All right. So once let me show you the code of this DaVinci .v. Very simple code. Okay, so we define the ports, define all the wires, the output, the address, read, write, clock reset is the input. My memory okay, this is the parameter we are kind of supplying down till the memory level. Okay, so remember in the TB we define the parameter as some, like let's say refib.dat. So instantiation time, it will become a refib.dat, and then when it instantiate the memory, we are passing that parameter, this current parameter, to the setting the parameter to the memory itself. So now with this instantiation, the parameter for the DaVinci system memory file is refib.dat, and then it will supply that refib.dat and set that to the parameter memory init parameter for the memory module itself. So memory module now starts going to load your refib program into its memory on a reset signal. Okay, and we instantiate a processor. Okay, so it's basically, it was coming from the previous project, so we named that as a section 5. I'll probably later in the next semester I'll just take out the section, we just do it approximately. So don't worry about this naming, but this is the process instantiation, and we just teach the data, address, read, write, clock reset signal between them. Okay, just as this as this diagram schematic says, right? We just teach those signals. All right, so this is all. This is a very small file. I didn't want you guys to bother about writing that, and this needs to be very carefully stitched. If some connection is wrong, then we suddenly get into a situation where you know you are doing correct modeling, but nothing is working because your connection is wrong. So that's okay. You don't need to touch this program, and let's go forward with the other things. Okay. Now the processor memory model we already discussed in the left wipe. That's the same memory we are sticking it here. Okay. Now processor.v is again a bunch of connections. So I didn't want you guys to go and bothered about this connection. It has to be very careful about this connection, and this is well tested from the last semesters. So just take it as it is. No change needed. Okay. The primary inputs are the reset and clock signal again for it, and outputs are basically mem write, mem read, memory address, and of course we have a bidirectional memory data which is being fed into the control unit. We instantiate a control unit, register file, ALU. Okay, so that's all we do here. Let's look at that processor.v. Okay, all right, so processor.v, here we are again defining the ports, defining the output address read write, in out as a data from the memory in out, and input as a clock and reset. Then we have some internal net section also, which is basically to connect between the control unit, register file, and ALU. Okay, so we have this ALU operation, register file address for write, register file address for R1 and R2. Remember, register is 2-port. We'll describe that in a minute. And RF data, register file data for write, register file data for read 1, R2. Those are all internal. Remember this one. These are the signal, all internal. These are all wires for us. Okay, only ports input ports are these, output ports are these, in out data is this. Everything else is kind of internal wire to us. So we are defining each of them in that specific file. Okay, and then we are just stitching it through the port and the wire. We are stitching all of them, and that is the whole system. So once we're done with the processor core, then we have these files to work on. Okay, register file, ALU file, ALU we already, I hope you guys are done with this by now, and the control unit. So we'll discuss more in later, maybe in the class, but basically control unit implementation for the control unit is basically cycles through the state like fetch, decode, execute, memory access, write back. So fetch mode, it issues that read signal with the instruction address of the next instruction address, and it reads back. Okay, decode is basically you take the instruction value, parse the instruction code, and determine what needs to be done. It's kind of that. Execute issues the control signals to kind of like, and basically also decode also involved that step. Also we are reading the register file, so we issues the register signals, register read write, register read address, write address, whatever needs to be done, and get the data back in the controller. And execute is the basically you're controlling the execution of the ALU, like you are setting the operation, plus, minus, division, multiplication, whatever, whatnot, those 7 or 8 functions we define there, setting the operands and taking the result out of that. Memory access, in case of load word or store word, you go and load the map from the memory, so you again issue a read address for the data for the load word, read signal, and get the data back in the control unit from the memory. And of course store address will go and involve the data to be written there, and write back if there is a not load word and store word, all other instruction basically do something right back into the register file, so result the write back into the register file. Okay. So now we'll look at those piece of code which needs to be complete in a minute in the model sim, but to finish that, let's look at the test strategy. So we defined a memory which supports insertion of memory from the external file. We do a system test. Okay, write assembly code. Again, sorry, this is a typo. This is to be CS147 DV. It was Seco 5 was previous semester language, but anyway, it is a similar thing. So in your CS147 DV instruction set, which performs operations, stores results, which actually covers all the things, convert them into corresponding machine code. Okay, you know how to do that in hand. Create the memory data file, loading the program from the system startup address, run the system with the new program code, dump the relevant data from the memory section, inspect if the program created a right result or not. Okay, so we write our program, convert it into the machine code, load the program, and make sure your program actually stores something in the memory as a result, so that you can test it out, you can dump it and see it, the result itself. Okay, so we'll now switch to pure model sim mode and try to breeze through, go through, walk through those the other files. One point is a clock generator. Okay, so it's very simple. It is just an output port. It has a register which is initially set to 1, and always a system half clock period which is defined in the project system, right? Clock period 10, half clock period is system clock by 2. So each half clock period you invert the clock. Okay, and see, we have actually given a non-blocking assignment here, but it doesn't matter. Just an example of non-blocking assignment in the data flow model. So there's a clock generator. Now register file. Okay, so remember, register is a two port, two output port. So it doesn't involve a in-out like a memory. So in-out is basically very complex to operate, a little bit complex, like because it involves the high Z state and stuff like that. This is straightforward. Okay, your input is read, write, clock reset, of course data bus to be written, and of course there are 3 type of address bus: address for R1, R2, these are for the read address, to read address, and address write. Okay, and output is basically your data R1 and R2, right? R1, R2. So what you need to do is basically for each reset and negative clock, you need to do the similar thing as the memory does. You also need to possibly add storage, like the memory. Okay, the 2-dimensional storage, but it is in case this is like 32 bit by 32 lines, right? So for that, and add data return register, just like the memory, right? And then you basically go and add data register, and then on the read signal, you basically read these 2 address of the register, like it could be 0 to 32, nothing else, right? It is a 5-bit address. So you read that location in the storage and write the content in the return register. So you need to have 2 registers for returning 2 data, which is connected to the data R1 and data R2. You can simply define another 2 register which is with the same name, data R1, data R2. Then you define data R1 equals that storage location at R1, data R2 equal to that storage location address R2. That's all. For the write operation, what you need to do, if it is a write, then you basically address W location of that your storage. You simply write the data W back. Okay, so it is very similar. So please go and complete this file and make a test bench of this register file register test bench, like similar to the memory test bench. You write something into the register and read it back and see. Maybe one simple test, like write at the register with their address. Okay, so register 1, write 1, register 2, write 2, register 32, write 32 there, and then for each of them in a for loop, read back the content, and content returned must be same as the address value, right? So register 1 will return a 1, register 2 will return 2, register 32 will return 32. So this is one simple test strategy. So go and write the test bench of this, very much similar to the memory test bench, but less complex. It doesn't involve uploading the memory and stuff like that. And reset is pretty much similar. You just, in a for loop from 0 to 32 address or whatever, you just write 0 in the storage location. Okay, so register file. Now ALU, as I described earlier, let's quickly look at. We have added 0 port, which is status. Apart from that, everything else is very much same as a project 1. You can pick up the code from the project 1, stick in here, and then just add the code for the 0. So 0 flag will be 1 if the result of the operation is 0. It will be 0 otherwise. Okay, this flag value will be 0 otherwise. All right, so this is the ALU file, and then we talked about the processor file already, and from that, let's say no, processor file, control unit. This is the most important file, control unit.v. So it has all the ports as in the schematic, shows in the schematic, and then what it has is a state machine instantiation, which supplies the state of the processor. So let's look at the what is the state machine. It takes the clock and reset signal. So on reset, it has to be starting from the fetch. Right? Remember, we have these 5 state here: fetch, decode, exe, mem, wb. So on reset, it has to proc has to supply becomes a fetch. Okay. So what you need to do is basically implement a state register is the same name as output, and initialize is as a proc fetch. And on reset, that is reset equals 0, you just get it done. So negative edge of the reset, if it is reset 0, then make the state proc fetch, state equal to proc fetch. Else, like so it is for it will be like always at positive edge of clock or negative edge of reset. Okay, and after that, in the beginning, what you need to put there is basically do the reset. Basically, if it is a reset, then set state assigned to the proc fetch, assign, just put that equals the proc fetch. And then if it is not, then it depends on the previous state. If the previous state is fetch, make it, if the previous state is fetch, make it decode. If previous state is decode, execute to memory to write back to fetch. So it goes in a cycle, this step. I think in the latter section, I think lab 7 or 8 maybe, we describe a state machine. We see how to implement that. It would be pretty much similar to that state machine implementation. So once we have the state available, then whenever the proc state changed, or maybe you can actually just change it to the clock, positive edge of clock, like that, of clock. Okay, so whenever it is there, basically what you need to do, depending on which state, you need to issue the signals correctly. Okay, if it is a fetch state, okay, so that means your memory read from the from that location, from the next instruction address location. Okay, and then so each of the state has to issue different control signal to either memory or register file or the ALU. So so we'll come to, once we come to that point, we'll discuss more about this. Okay, this part. So I think that's all you need to know about the project 2 right now. So at this stage, I would expect you guys to complete ALU, complete the register file. Okay, then we'll go and complete the state machine, and after that we'll start coding here in this block. Okay, so that's all, and hopefully you guys started already working on that project. Good luck with that, and if you have any question, let me know at the class.